Hello everyone, it's Mr. Lopez once again, and we're doing chapter 2 today. We're only going to be going through half of chapter 2. I've kind of decided to kind of break the chapters in half a little bit since we're still kind of getting the lay of the land. That might change later on this semester, and maybe we might do full chapters a week. But for now, I want to go ahead and stick to the half a chapter a week way that we've been going. Now, for this chapter, we're going to be looking at kind of the chemical basis of the environment. We're going to be looking at things at like systems and feedback loops. Some of the laws of energy. Some of these things you might have heard before, you might have learned before in your chemistry classes, even in some of your earlier biology classes, or if you've taken physics, some of these physics laws that we will be talking about might have been covered before. So the first thing this chapter does, and we'll find this in almost every chapter, it takes a look at a case study, just to kind of get a real world scenario of what's happening. And so in the first chapter, we looked at Apple Island and how they were dealing with overfishing and destructive methods. Here we're looking at something that's a little bit closer to home, and we're looking at how to work to rescue an ecosystem. And so we're looking at a particular region around Chesapeake Bay, which is that blue body of water that's been highlighted, and how it's been dealing with, over the years, a lot of pollution that's coming from a combined 6 states. And you might look at the map and wonder, well, how is it getting pollution from places like New York and Pennsylvania? And you can see that there's a large river that runs through these states that tends to carry a lot of pollution in its water. And so over the years, they've been seeing the depletion of overall wildlife, things like fish, oysters, crabs, because there is a rise in nitrogen levels as well as phosphorus levels. Now, we normally need nitrogen and phosphorus to survive. All wildlife needs it. But because of pollutants like sewer drainage and just overall air pollution, we're getting an overabundance of nitrogen and phosphorus in these locations, and that overabundance is causing kind of like a suffocation, if you would compare it to that, in that body of water. So what's ended up happening is that over the past couple of years, the EPA, particularly under President Obama, has really kind of tried to step up and kind of lead the charge in making these 6 states kind of become responsible for what they're doing to the body of water and how to be able to better stabilize the system. Because, of course, they're not going to be able to return it to its original pristine state. But, it does matter. They get a lot of their fish, a lot of their food come from this body of water, Chesapeake Bay, and a lot of tourism dollars, things like that. And, of course, they want to make sure that it looks beautiful, that it's habitable. And so, really, this is a good example of how we would approach various other similar situations across the United States and across the world. And that is, having people really take responsibility for what's going on in their areas. So I encourage you guys to read that case study. It's a very interesting case study, and more than likely I will be applying it soon to an assignment. So make sure that you keep an eye on that. Now, there was a quote that was said by Robert King Merton that I really like. It says here, most institutions demand unqualified faith, but the institution of science makes skepticism a virtue. And this kind of ties into what we talked about in chapter 1 and how a lot of science has to be evidence-based. And so here, in particular with the case study that we just saw, we're looking to see some evidence that's going to show some kind of results. And so we kind of have to be a skeptic up to the point of actually seeing some results that we like. Okay. So this chapter, particularly the first 3 sections, are going to be focusing on how chemistry plays a large role in environmental science. We talk a lot about greenhouse effects. We talk about carbon emissions in the atmosphere. What does all that mean? Why do we use carbon emission? Why do we use greenhouse gases? We talk about ozone layers being depleted. These are just fancy words to some people, but of course there is an actual chemistry understanding of what these words mean. So we're going to be focusing on that in these next 2 to 3 sections. So section 1 talks about how systems work. And this is a system is a network of interdependent components and processes with materials and energy flowing from one component of the system to another. And so a good example of a system, of course, is an ecosystem. And we've all heard the word ecosystem, and all that really refers to is an association between various species and their environment. So in other words, how do we, the human beings, interact with the squirrels, with the ducks, with the dogs, with the trees and the grass and the air around us? That is what it makes an ecosystem. And so I'll give you the definition, of course, that's listed here. And it says here, an ecosystem is a complex assemblage of animals, plants, and their environment through which materials and energy move. In a short bit, we're actually going to talk about the first law of thermodynamics, which states that matter can neither be created nor destroyed. And that kind of ties into what an ecosystem is. We just see a lot of energy being moved from one organism to the next. For example, when a human being dies, they decompose, which means that our energy is then transferred to the soil, which then, of course, feeds the plants, which then, of course, feeds the rabbit or the cow, which then is fed to another human being, and the life cycle continues. So that energy just continues to flow through this ecosystem. And of course, we have a lot of different terms that can be used when describing a system. For example, a simple system consists of state variables or compartments which store resources such as energy, matter, or water. And it also has flows, or the pathways by which those resources move from one state variable to another. And this, again, kind of refers to how we pass along the energy. In this case, I mentioned a while ago how the energy that comes from a decaying body would then be transferred into the circle of life, if you'd call it that. And so we have a great example of an image here of what an ecosystem looks like. And again, you see the circle there that represents how the energy is flowing. And so we see that, if you know anything about photosynthesis, which refers to how plants capture sunlight and create energy. So the first place where energy comes from in this particular image is, of course, the sun, which then is converted into photosynthetic energy by the plant, which then, of course, feeds the herbivore, in this case, the rabbit, which is then predated or, caught by a fox in this case, and eaten. And, of course, the fox in this case dies and begins to decompose, whether it's through, fungi or other organisms, bacteria, that break it down into eventually nothingness and then feed the soil, and this life cycle continues. So that's kind of what it means, how a system will flow with a lot of different variables in the midst. And of course, there are different types of ecosystems. For example, the one that we're most familiar with are open systems. Open systems are those that receive inputs from their surroundings and produce outputs that leave the system, which is this image that we just saw a while ago. Let me go backwards here. That is a good example of an open system. We have energy that's coming from an external source, in this case, the sun. And of course, the energy continues to go through various organisms, which will lose energy in the form of heat and eventually decomposition. So that's a good example of an open system. Now, however, we do have some examples of closed systems. You usually tend to see closed systems in things like laboratories, where you're trying to control every single detail that goes into your experiment. Another close example to a closed system would be like an aquarium, where you're keeping specimens within a confined environment, where you decide how much they eat, where you decide how much vegetation is available. Of course, that's not a completely closed system, because there is still heat escaping the aquarium thanks to their constant movement and swimming. But the true definition of a closed system is a closed system exchanges no energy or matter with its surroundings. So it's totally enclosed. And this next term we saw in chapter 1, and that is throughput. So throughput is a term we can use to describe the energy and matter that flow into, through, and out of a system. So again, the previous image that we saw of a rabbit eating a plant, which then itself was eaten by a fox, which then itself was decomposed. We see energy constantly flowing through these ecosystem, because we have to realize that whatever energy the plant makes is not entirely consumed by the rabbit. And the energy that a rabbit makes is not entirely consumed by the fox. Energy is always being lost in the form of heat. For example, every time that we go running, every time you start to feel hot under the collar, you start to sweat. And what ends up happening is you're losing heat to the atmosphere, which you can never regain again. And that is what throughput is. Energy is moving through you, into you, and out of you. And of course, we will talk about that a little bit more in depth later on in the chapter. Now, what helps to stabilize a system? Well, we have things that are called feedback loops. These are loops that respond to change in the system. Systems function in cycles, which each component eventually feeding back to influence the size or rate of itself. And so think of it as consequences. We always say that things either have a good consequence or a bad consequence. Sometimes if you're caught in a lie, that'll have a negative consequence. That is a feedback mechanism, which we've all experienced in a variety of ways. So here we see what a positive and a negative feedback loop is. It says here a positive feedback loop tends to increase a process or component. So here we see another perfect example of what a feedback loop looks like. Let's say that we plant a garden that is abundant in vegetation. And all of a sudden we start to see a rise in rabbits and other critters that start to eat away at the garden that you have behind. That is a positive feedback because of your increase of resources. You now have an increase of rabbits in this case because they are no longer having to compete for resources. So that is considered to be a positive feedback. However, the more and more and more rabbits you create and the more they consume the garden, then you will have less vegetation available, which of course that is a negative consequence or a negative feedback. And that of course also plays a role in determining how many rabbits are now available because the less vegetation you have available, the more competition that creates, and you have instances of starvation, of competition, which leads to a decrease in rabbits, which of course that's another example of a negative feedback. And the cycle continues. Well, now that you have a decrease in rabbits, you now have less animals trying to eat the vegetation. And so you have an increase in vegetation, and therefore the cycle continues all over again. So we have a constant back and forth between negative feedback loops and positive feedback loops. And you'll see a lot of this even in your own personal life, which again, we're not looking at maybe resources, but you might be looking at things like attitude and behavior. These are things that have negative and positive feedback loops. So I encourage you guys to think about this a little bit in detail and see what kind of things you can think of that would apply to positive and negative feedback loops. So again, we look at why these feedback loops are so important. A lot of times when we look at places like emergent properties, what ends up happening is we see systems that have kind of created a barrier where they can kind of protect their area, their region, because it's a result of a feedback loop. And here we see the term emergent properties. It says here emergent properties is used when the characteristics of a whole system are greater than the sum of its parts. For example, we're looking at an image here of mangrove forests. Mangrove forests, they grow along coastlines throughout the tropical world. Because their direct economic value can be modest, thousands of kilometers of mangrove-lined coast have been cleared to make room for shrimp ponds or beach resorts. But the mangrove forest provides countless indirect economic values. For example, they trap a lot of sediment and they stabilize a lot of mudflats from simply just falling into the body of water. So without those mangroves, when they get depleted, it can cause a negative feedback, which can then result in pollution, indirect pollution of the body of water because they're no longer there to stabilize the ecosystem. They're no longer there to protect small fish and other marine species. So again, that's what emergent properties are. Now, 2.2 talks a lot about kind of basic chemistry and physics. I mentioned early on in this video that in order to understand environmental biology, you have to have a simple grasp of just basic chemistry and understanding what makes up life. So for example, most of you have probably heard this definition before, but we are all made up of matter. And matter is anything that takes up space and has mass. We all have weight, so therefore we have mass. And we all take up space, therefore we matter. Because we are matter. And of course, we all already know that matter, at least on this earth, exists in 3 different states. And that is solid, liquid, and gas. There is a 4th state known as plasma, but we mostly see that in other celestial bodies like the sun that we don't actually get to interact with here on Earth. And so a good example that you would have thought about that is in a solid, liquid, and gas is water. Of course, water in itself is always in a liquid form, but when you freeze it, it's solid, and when you overheat it, it evaporates into a gas. And so, as I mentioned earlier, one of the main principles of physics is what's known as the conservation of matter, which states that under ordinary circumstances, matter is neither created nor destroyed, but rather is recycled over and over again. And I used that example earlier about the dead person that's rotting away, feeding energy and nutrients to the soil. That is an example of matter being converted into a different form, but never truly being lost or destroyed. It's just being recycled over and over and over again. And most elements do have predictable characteristics. And what does that mean? Well, first we have to understand that matter consists of elements. We all are aware of things like the periodic table, which display all the known elements on this earth. And all elements are really made up of the same type of atoms. So this is here an element of phosphorus or nitrogen, which are substances that cannot be broken down into simpler forms by ordinary chemical reactions. So once you get an element of nitrogen, you can't break it down any further. That's as small as you're going to get. You can't get any smaller than the atom, which is the smallest particle that exhibits the characteristics of an element. So if you have an element of nitrogen, for example, you can have 100 different atoms of nitrogen, but they all have to be the same. They all have to be nitrogen. That's what makes it an element. You can't have 100 atoms of nitrogen and one atom of phosphorus, because that is no longer an element. That is now what we call a molecule, and that completely changes the term. So make sure that you understand the difference between an element, an atom, and a molecule. Now, of course, the atom itself can be broken down into smaller parts. The atom is composed of a nucleus, which itself is made up of positively charged protons and electrically neutral neutrons. These two subatomic particles are what make up the nucleus of an atom. Hovering around the nucleus is where we find the negatively charged electrons. So what helps keep the electrons stabilized and in place is the fact that we have positively charged particles known as protons. Think of it as a magnet. Magnets, positives are always attracted to negatives, and they always want to stick together. Same principle applies here. You're going to always have positively charged protons attracting negatively charged electrons, and they always want to stick together. And so here we have a detailed image of what a carbon atom looks like. Carbon has an atomic number of 6, meaning that it has 6 protons. And so if you have a neutral atom, it's assumed that you have to have the same amount of electrons as you have protons. So in this case, you have 6 electrons to 6 protons because it balances it out. And of course, carbon has an atomic mass of 12, meaning that you have 6 neutrons as well. So you see an image here of the nucleus of the atom. They're all confined within the most central part. And then on the outer parts of the atom, you have the electron cloud, which in this case, carbon has 6 electrons. So you see 6 little gray circles there that represent the electron particles. Now, it says here, elements have a unique structure. And you'll see some terminology that I just mentioned, like not even 10 seconds ago. It's here, each element is listed in the periodic table according to the number of protons per atom. So they go in increasing order. For example, the very first element that you'll run into in the periodic table would be hydrogen. Hydrogen only has 1 proton, therefore its atomic number is 1. The next one in line would be helium. Helium only has 2 protons, therefore its atomic number would be 2. So anytime you see the atomic number, that refers to how many protons that particular element has. Now, the number of neutrons in the atoms of an element can vary slightly. Some people falsely assume that you should always have the same number of neutrons as protons. That's not true. The best way to determine how many neutrons you have is to subtract the atomic mass from the atomic number. So, for example, let's look at carbon again. Carbon has 6 protons, meaning it has an atomic number of 6, and its atomic mass is 12. So if you subtract 6 from 12, you get 6. So that tells you that you have 6 neutrons as well as 6 protons. Occasionally, you will find something that's called an isotope. So, for example, let's look at carbon again. An isotope is a form of a single element that differs in its atomic mass. In its most natural state, carbon has an atomic mass of 12. So we call that carbon-12. However, there are some cases where you find carbon-13 and carbon-14. Carbon-14 in particular is really useful because we call that radioactive carbon, or we use it for carbon dating. In other words, being able to tell how old something is, we'll use that particular carbon. And so what the 12, 13, and 14 refer to is the atomic mass. So in carbon-13, you still have 6 protons, but you now have a 13 mass. So if you subtract 6 from 13, you now have 7. So you have 7 neutrons in carbon-13. And again, if you do carbon-14, you have an atomic mass of 14. You subtract the 6 protons, and you get 8. So that means that you have 8 neutrons for 6 protons. And that is what we refer to as an isotope. And so the charges are what keeps everything together. As I mentioned before, you have positive charge and you have negative charges. They're always going to want to stick together and remain close to each other. However, there are some cases where an atom will either give up or receive an extra electron. And so when that happens, it changes the overall charge of the atom that you're looking at, either giving the atom a negative charge if it loses an electron, or it gets a positive charge if it gains, or if it loses an electron, and it gets a negative charge if it receives an electron. So we call these ions. Ion is any kind of charged atom. So negatively charged atoms are known as anions, while positively charged ions are cations. And the way that it was taught to me in college, and it might sound kind of silly, but I was told that cats have paws, so paws are positive. So cations, cats are positive. And I get it, I know it sounds silly, but if it works for you, then I would highly recommend that you use that as well to remember that cations are always positive. So a good example of an ion is sodium and chloride. Both of these individual atoms are normally found in a gas state, but when combined together, they form sodium chloride, which you know as table salt, and that is a solid. So what ends up happening is that a sodium atom will give up an electron, making it now a positively charged ion or cation. So it's represented as Na+. Chlorine, on the other hand, will easily accept an electron, therefore giving it one more electron than it has protons, giving it a negative charge or making it an anion. And so these two ions have opposing charges. So when they're in the same proximity, they will be attracted to each other, therefore creating sodium chloride or a new ionic bond. Now it says here that atoms of elements often join to form compounds. A good example of a compound would be O2. Okay? It says here atoms of elements often join to form compounds or substances composed of different kinds of atoms. So, for example, we know H2O. H2O is a compound. NaCl is a compound because they're made up of different kinds of atoms. A molecule is just here a pair or group of atoms that can exist as a single unit that is known as a molecule. Now, where people get confused between the word molecule and compound is that a molecule can be either the same type of atom or different type of atoms. So, for example, H2O is made up of 2 different types of atoms. It's got 2 hydrogens and it's got 1 oxygen. That is a molecule. The oxygen that we breathe is O2. That is also a molecule because you have 2 atoms, even though they're the same. However, O2 cannot be called a compound because compounds have to have different kinds of atoms. So while water is a compound and a molecule, oxygen can only be called a molecule and not a compound. So I mentioned earlier with the example of sodium chloride, we have 2 atoms with opposing charges and they link together or they are attracted together, they form what's called an ionic bond. Those bonds can, they're relatively strong, but they can still be broken. Another type of bond that we see in chemistry is what's known as covalent bonds. So while ionic bonds either gave up or received an electron, covalent bonds prefer to share their electron. They don't give it up or receive an extra one. They will share electrons. So therefore, you should never see charged particles when it comes to covalent bonds. And so here we have an image of some common molecules that I was just mentioning. For example, hydrogen, oxygen, nitrogen. Those are what we call molecules but not compounds because they're the same. And then we see other ones that are considered to be both compounds and molecules, such as hydrochloric acid, water, carbon dioxide, methane, and so forth. So make sure that you can differentiate between what is a true molecule and what is a compound as well. Now, understanding charges such as positive and negative charges is also very useful for understanding the concept of acids and bases. And I'm sure that again you've all heard of acids and bases. We've all heard of like lemons being acidic or tomatoes being acidic. But what does that actually mean? What does it mean to be an acid, or what does it mean to be a base? So it says here that substances that readily give up hydrogen ions in water are known as acids. So the more hydrogen ions you have, the greater the acid. So you can go from 7 down to 1. All that means is that you have more hydrogen ions at 1 than you have at 7. And substances that readily bond with hydrogen ions are called bases or alkaline substances. And what ends up happening is that they end up also releasing hydroxide ions or OH negative ions. So this is on the other end of the spectrum. So here you're removing hydrogen ions from the solution that you might be working with, causing a base. A good example of a base would be like bleach, sodium hydroxide. And so the scale that we use to measure them, of course, we call this the pH scale. Acids have a pH below 7, while bases have a pH greater than 7. And of course, a neutral substance has to be exactly at 7. So even if it's at 6.99, you are technically working with an acidic substance. And if you're working with a substance that's 7.01, you are technically working with a basic substance. So even if it's just at 7, that's the only time that you can actually call something neutral. And a good example of a neutral substance would be like pure water. Now, I'm not talking about tap water or the water that you buy at the store. I'm talking about pure water. Pure H2O is what you would have at neutral pH. And so here we see the pH scale, and we see some examples of some of the products that we see, at the various ranges of pH. So, for example, at pH of 6, your saliva is at pH 6, which is not very acidic. Or you go upwards and you see baking soda, which we all have used baking soda before. That is slightly basic. So every pH unit that you go up or down, what's happening is you're increasing the amount of hydrogen presence by 10-fold. So for example, if you go from 7 to 6, you're increasing the amount of hydrogens at 6 10 times than what you would find at pH of 7. And that continues to increase at an exponential rate of 10 power every time as you go closer to 0. That's why on the left-hand side of the scale, you see 1, 10, 100, 1,000, 10,000. You're having an increase of 10 power every time that you go up 1 unit. Now, another important thing to understand about life in general is understanding what an organic compound is, because most living things tend to be what we call an organic being. I'm sure you've heard of the term organic before, like when you go to the store and you see that something is completely organic or natural. That kind of is a little bit different than this organic. Organic here refers to anything that's made up of predominantly of carbon atoms. So it says here, carbon is a special element because chains and rings of carbon atoms form the skeleton of organic compounds, the material of which biomolecules and therefore living organisms are made. The 4 major categories of organic compounds in living things, particularly in us, are lipids, carbs, proteins, and nucleic acids. And I'm sure that most of you have heard of these 4 different categories before. Nucleic acids are things like DNA and RNA. We've all heard of proteins. We've all heard of carbohydrates or carbs. And lipids, of course, is where we find things like fats. And so those 4 categories are super important to all life. And anything that's not made up of carbon is what we call an inorganic compound. So we heard about sodium chloride earlier. Sodium chloride has no carbon in it. It's just 1 sodium and 1 chloride. Therefore, that is an example of inorganic compounds. Excuse me, I went a little bit too far there. So here we get a little bit of definition about what these 4 categories are of organic molecules. And so lipids, as I mentioned before, includes things like fats and oils. Think of butter or our own belly fat or vegetable oil. That is all the same thing. And lipids are known to store energy for cells and provide the core of cell membranes and other structures. So if you've studied biology before, you know that our cells are made up of a phospholipid bilayer membrane that is made up of fats or lipids. Carbohydrates are our main source of energy that we use to survive. It says here, carbs store energy and provide structure to cells, because usually we tend to find sugars and starches as carbs, and this is good for our body. Of course, overeating that can be very bad. It says here, they usually consist of a long chain of simple sugars like glucose. And if you ever heard of glucose before, you usually refer to it for diabetics. They're always having to check their glucose levels because Glucose is an important compound that we need in our body to survive. And so it needs to be regulated constantly in our body. And so we continue here with proteins. Proteins are composed of chains of amino acids folded into complex 3D shapes. Protein provides structure to cells and are used for countless cell functions, including enzymes. So enzymes are a unique form of protein which helps speed up the rate of reactions. If we didn't have enzymes in our body, there'd be a lot of processes that would take days and months to do. Therefore, we would constantly die easily. And so, thanks to enzymes, these processes can function at a more reasonable pace and therefore keep us surviving. Proteins are very, very important, and especially if if you've known a bodybuilder or somebody that works out a lot, you know that they're always worried about how much protein they consume, and it's for a reason because protein helps to repair cells that you're constantly tearing when you work out your muscles. And then, last but not least, we have nucleic acids, or otherwise known as nucleotides. Nucleotides are complex molecules made up of a 5-carbon sugar, one or more phosphate groups, and a nitrogen-containing base. And so these are very important because in the case of DNA, this is where we get all our genetic instructions. So if we didn't have DNA, we wouldn't be able to have offspring or even ourselves be alive because there would be no instructions to create us. And so DNA and nucleotides are a very, very important organic molecule. And so here we see an example of these 4 different organic molecules. Now, this is not a chemistry class, so I'm not going to ask you guys to memorize this structure, but I just want you to be aware that there are different types of organic molecules. And you notice, if you look closely at these images here, there's a lot of carbon, these little gray circles, in all 4 of these organic molecules, just to show you the importance of carbon in organic molecules. And so here we see the double helix structure of DNA, which again is important for us because that's where we get all our genetic information, which is littered with carbon in there. All those little gray circles represent carbon. So again, we see the importance of carbon in all life. Now, of course, once you move up the atomic level, we've still been looking at atoms so far and molecules, but now we're going to move up to the next level in biology, which is, of course, cells. Cells are the fundamental units of life. And in fact, cells are considered to be the smallest thing that can be considered life. An atom cannot be considered a living thing because one of the key tenets of life is the ability to reproduce. And atoms cannot reproduce. They can only exist as they are always. And so cells can reproduce. The fact that we ourselves were born from 2 cells merging and becoming 1,000,000 cells, that represents life. And so here it says all living organisms are composed of cells, minute compartments within which the processes of life are carried out. And of course, the cells themselves are made up of a variety of molecules and atoms, which help to kind of create the processes that we need for daily life. And some of the main components other than carbon that we need as key nutrients are nitrogen and phosphorus. And if you recall, in that first image that I started off with in this chapter, in the case study talking about Chesapeake Bay, we see that nitrogen and phosphorus plays an important role in life. And so we need to make sure that we keep it at an abundant level, but of course not overly abundant where we destroy this planet. It says here that carbon is captured from the air by plants, and oxygen and hydrogen are derived from air and water. All the other elements that we get, like nitrogen and phosphorus, are obtained from the things that we eat because they are necessary components of all the organic molecules that we need. Things like protein, lipids, fats, and nucleic acids. And so the food, the meat, the plants that you eat will always refill these resources that you need. And so you see here at the very bottom of the last bullet, it says, low levels of nitrogen and phosphorus often limit the growth in ecosystems where they are scarce. So when you have low nitrogen, low phosphorus, you tend to see low vegetation, low animal life, and eventually you see a dead ecosystem. So we see the importance of nitrogen and phosphorus in an ecosystem. And however, you see on the bottom here, it says here, abundance of nitrogen and phosphorus can cause runaway growth. In other words, an overabundance of these things leads to just too much growth. And again, you look at the Chesapeake Bay example. What happened there was because of all the excess nitrogen and phosphorus in the water, you had an overabundance of algae growing, and the overabundance of algae then led to the plants in the water being blocked. They didn't have access to the sun, which led to death of these plants, which then led to death of fish. So you see that it can have inverse effects. So you have to catch a good equilibrium in order to make sure that you maintain a good, stable environment. And then we move to the last section that we'll be covering today, and that is energy. Energy is defined as the ability to do work such as moving matter over a distance or causing a heat transfer between two objects at different temperatures. And you gotta remember, energy is neither created nor destroyed. It's just constantly in movement, constantly taking different forms. The forms that it takes can be things like heat, light, and chemical energy. And so, of course, you might have heard this before, but there are two types of energy that we talk about, and that is kinetic energy and potential energy. Kinetic energy is defined as energy in motion. So we look at this image here, we see a pretty still body of water that is then flooding over a waterfall. Well, in that body of water at the very top of that image, that is what we call potential energy. In other words, energy that has potential to do something, but at this moment, it is not doing anything. Think of it as yourself when you sit on a couch. When you're sitting on a couch, you have the potential to do something, but as of right now, all you're doing is sitting down. It is when you decide to get up that kinetic energy starts to take form, and that is because you are now moving. And so we see the waterfall represents kinetic energy because we see water moving through, bodies of rocks and things like that. So we have constant movement. And as I mentioned before, potential energy is stored energy that is available for use. So anything that is immobile, like a rock, is a good example of potential energy. Once you kick it, it becomes kinetic. But even itself, it will not do that unless you actually move it yourself. And then, of course, we also see chemical energy, which is a good example of that is when you eat food and you digest it, it changes. It now becomes nutrients for your body, and it becomes chemicals for your body, which will then move throughout and feed you. And so some of the basic energy concepts you have to understand is understanding what heat is, as well as some of the laws of thermodynamics. So heat describes the energy that can be transferred between objects of different temperatures. For example, you can actually feel when somebody has a fever because they are emitting heat. So that heat is being transferred to your hand when you touch their forehead or their skin. So that is a good example of heat. Okay. And I mentioned before, the first law of thermodynamics, it refers to the law of conservation, which we saw earlier, meaning that the energy can neither be created nor destroyed. It simply changes shape and form. However, the second law of thermodynamics states that with each successive energy transfer or transformation in a system, less energy is available to do work. And so what that means is, if you recall, we had an earlier image where we saw the sun creating energy for the plant, which then fed the rabbit, which then fed the fox, which then died and fed the soil. Each time that there is a transfer of energy, for example, when the rabbit eats the plant or when the fox eats the rabbit, there's less energy that is available than before. And that is due to the second law of thermodynamics. And what ends up happening is we lose energy due to entropy. So the second law recognizes that disorder or entropy tends to increase in all natural systems. So for example, when heat rises and it becomes warmer, we have an increase in chaos or increase in entropy. So we'll stop right here. Make sure that you look for your assignment on the folder that is found under the chapter 2. And if you have any questions or concerns, please feel free to call me, and I will do my best to get back to you as soon as possible. Thank you, and you all have a great day.